So we start with the definition of a category. A category C consists of the following. So the category C consists of the following data. One is, the category C consists of a class. So this class we write like this. Notice that I am saying a class. This class belongs to some universe. We are not going to define what universe it is, but just to make sure this is different from set. The elements of this class will be called objects of the category, and that is why sometimes we will write this class as ob of C, because the elements of this class are nothing but called as objects of the category. Second is, for every pair A comma B of objects, there is a set C A comma B. So this is a set. Notice that this is a set, and in one we have class, in number two we have set. This is important. The elements of this set will be called morphisms or arrows from A to B. Now we will often write C A comma B as home A to B. So this is so that we remember that, for example, in rings, if we work in category of rings, the morphisms are nothing but homomorphisms. So we have taken the motivation from there, but C A comma B is probably a better notation. So part 3 is, for every triple A comma B comma C of objects, there is a composition law. So it's just like composing two functions. We have a composition law which composes two arrows or two morphisms. So how does it work? So you have an arrow here from A to B. Denote this arrow by F. B to C, we denote this by G. You compose them together, you get G naught F. F, G, and you get G naught F. So the above data is subject to the following axioms. So the first is the associativity axiom. So again we are given arrows H, G and F. So this associativity, this is associative. So this is the same as what we have written between G and F. So diagrammatically this is how it looks like. A to B to C to D, we have F, which is an arrow from A to B, G an arrow from B to C, and H an arrow from C to D. So we will write this down clearly. We can also call this morphism from A to B. G is a morphism from B to C, and H is a morphism from C to D. And B is the identity axiom. So we have the following equalities. F is an arrow from A to B, and if G is an arrow from B to C, the following equalities will hold. So diagrammatically this is how it will look. So you have 1b here, so you will also get f like this, and similarly for g. So let us now record some important definitions. The first one is, when is an arrow in the category an isomorphism? So we fix the category we are working in. Say we are working in category C, as we mentioned in the definition. So an arrow f from A to B is an iso. So this arrow f is an iso if there exists an arrow in the opposite direction, that is an arrow from B to A, such that the following two identities are satisfied. So of course this arrow from B to A is unique, and often we write it as F inverse. Second is monomorphism. So an arrow F from A to B is a monomorphism if for any, notice the word any, if for any GH, and these GH are nothing but arrows from some C to A. So let us write this down. So we are trying to say when this F, an arrow from A to B, is a monomorphism. So you have these any GH which take C to A. So these are arrows from C to A. And we have an arrow F from A to B. So obviously if we have this thing, if this thing holds, so F naught G and F naught H, if this holds, this implies, if this holds, then it implies G is equal to H. So in some sense, F is a monomorphism if there is a left cancellation of arrows. Similarly, we have epimorphism. So an arrow is an epi so this arrow is from A to B. So this arrow from A to B is an epi if for any G to G and H from B to C. So if there are G and H, any GH from B to C, and this condition holds, so you first apply F, then G, then you first apply F and then H. This would imply G is equal to H. So in sense, epimorphism implies the right cancellation of F. Now an important concept which comes up again and again is the opposite category. So opposite category is, there is nothing special about it. It has the same objects as the original category, and it has arrows in the, only the arrows get reversed, and that is what we will write down. So the objects are the same, and the arrows are reversed. So that is pretty much it. So category C prime is a subcategory of C. So category C prime is a subcategory of C if objects of C prime are subset of objects of C and these arrows in C prime are also a subset of arrows in C, as well as the composition in C prime is induced by composition in C, and also the identities in C prime are induced by those in C. So I have not written the identities in C prime are induced from C, but you should note that. When does this subcategory become a full subcategory? So first of all, this condition is satisfied and this one is satisfied, and the arrows have equality here. So again we have a subset in terms of objects, and composition and identities are induced from C, but we have an equality in terms of arrows. So a category is discrete if the only morphisms are identity morphisms. So only morphisms are identity morphisms. A category is finite if the family of all morphisms in C is a finite set. So the family of all arrows in C, so A, B could be any objects in C. So a family of all these arrows in C form a finite set. They are anyway a set, but they form a finite set. So category C is a groupoid if all morphisms in this category are isomorphisms. We have already defined isomorphisms in the previous slide. So now we have to come to certain examples of categories. So the first example to keep in mind is the category of sets. So the objects are sets and the morphisms are maps of sets. So the objects are sets and the morphisms are map of sets. So Russell's paradox shows that there is no set of all sets, and that is why we talked about the class of objects rather than the set of objects in the definition. So notice that in the definition I talked about class, not sets, for objects, because there is no set of all sets. So we want to avoid Russell's paradox. So another example is this category written as vec K of vector spaces over a given field K. So these vector spaces, so objects are these K vector spaces, and the morphisms are linear transformations. So you should think of Rn to Rm, and the matrix which takes them from Rn to Rm is the morphism. Then another example is abelian groups. So abelian groups are the objects and group homomorphisms are the morphisms of the category, say AB, which consists of abelian groups. Now if A is a ring, then A modules form a category which we write as mod A. So this is the category of A modules. So again, if we take A as just as a field, we obtain example number 2. If we take A as integers, we get example number 3. Now another example is category of rings. The objects are rings and the morphisms are ring homomorphisms. And for our purposes, 1 will be sent to 1. So another example is the topological space. So we will denote this by top. So the objects are topological spaces, morphisms are continuous maps, and homeomorphisms are isomorphisms in the category or category top. So let us write this down. Objects are topological spaces, morphisms are continuous maps, and isomorphisms are homeomorphisms. So another important example is of a partially ordered set. So a partially ordered set or a poset, this is a set S with a binary relationship. Yeah, this is greater or equal to sign is the binary relationship, and it satisfies the following conditions. First is reflexivity, then second is transitivity, and now we talk about transitivity. And the third is this equality which follows from x greater or equal to y and y greater or equal to x would imply x is equal to y. So these partially ordered sets with this binary relationship which is greater or equal to sign, this can be interpreted as a category. So again, this partially ordered set with a binary relationship, this can be thought of as a category. So the objects of the category are nothing but elements of the partially ordered set S, and there is a single morphism from x to y if and only if x is greater or equal to y, and there is no morphism otherwise. So let us write this down. So morphism if and only if, so morphism from x to y and it is a single morphism if and only if x is greater or equal to y and there is no morphism otherwise. So now I want to give examples of initial and terminal objects. So an object P of category C, so P is an object of category C, it is called initial if for all x, so if for all x which are objects of the category C, this holds. Yeah, from P to x, this is equivalent to a point, and basically what it means to say is that the object of the category C is initial if there is precisely one map to every object. So the point means that there is precisely one map from P to every object x. So if it is initial, there is precisely one map from every object to x. So dually we have the terminal object. So that would mean that there is precisely one map from every object to this terminal object. So this is also point, and it's equivalent or isomorphic to a point, means that there is precisely one map from every object of C to P, or you can say a terminal object is initial in the opposite category. So an object which is both, so this is another important definition, an object which is both initial and terminal is called the zero object. And it is denoted by 0. On this slide, we want to talk about terminal objects being unique up to unique isomorphism. The same is the case with initial objects. So we fix a category C and we consider two different terminal objects, and then we will show that these objects are, there is only a unique object and there will be a unique isomorphism if there is another terminal object. So let us fix this. So consider two terminal objects P1 and P2, and we will show there is, the terminal object is unique up to unique isomorphism. So since P2 is a terminal object, we have a single arrow from X to P2. Since P1 is a terminal object, we have a single arrow from X to P1. Now again, P1 is a terminal object, so we have a single arrow from P2 to P1, which we will write as, say, phi1. And since P2 is a terminal object, we have a single arrow from P1 to P2, which we will write as phi2. Now again, we can construct an arrow from P1 to P1. Yeah, so if you consider P1 as a terminal object, then we have an arrow from P1 to P1, which is the identity morphism. This also comes directly from the definition. And similarly, we have P2 to P2, again an identity on P2. But we have seen the morphisms to terminal objects are unique because we have shown on the previous slide is equivalent to a point. That means there is a single map. So one P2 has to equal to any other map which takes P2 to P2. So that is, you first apply phi1 and then you apply phi2, you end up at P2. So that has to be equal to 1 P2 by the definition of being a terminal object. Similarly for 1 P1, you first apply phi2 and then you apply phi1, you get to P1. And 1 P1 also takes P1 to P1, but since P1 is terminal object, we should have a single arrow, and that's why the equality comes in. So as a result, we have phi1 and phi2 are inverse isomorphisms, and that what shows that the terminal object are unique up to unique isomorphism, because from P1 to P2 we have been able to construct two maps which are inverse isomorphisms. So another definition we want to say is that a category C is a small category when its class of objects is a set. So for this course, we will always take categories as small categories. So I want to emphasize that we are taking C as a set, not as a class, and that is important. Secondly, notice this unique up to unique isomorphism is a special property which will come up again and again. So you should try doing the same thing with initial object. We will again do unique up to unique isomorphism in products and other things. So it is important to understand that what unique up to unique isomorphism means. So essentially, if you have something, some other object, you should be able to construct something like phi1 and phi2, which are inverse isos. and that is the point to keep in mind.